We will begin the session in a few minutes. Let us just wait for some time for other students to join. Okay, so let us begin with the session now. This is week 8, which is the final week of the NPTEL course on Calculus for Economics, Commerce and Management. So this is the last week of the course. It was an 8-week long course. I hope you have learned many of the basic concepts of calculus like limits, continuity, differentiability, and these concepts. So although this is the last week, we will have one revision class. So that will be the final video problem solving session. But this, according to the course, this is the last week. So let us get started with the first question. The function gx equals ax squared plus bx plus c, where a, b, c belong to the set of real numbers, are constants, has which of the following properties? We need to select. Option A unique point of inflection for any choice of a, b, c belonging to R. B, no point of inflection for any choice of a, b, c belonging to R. C, no point of inflection for the choice of a equals 0 and any choice of a, b, c belonging to R. or D, infinitely many points of inflection for the choice A equals 0 and any choice of B, C belonging to R. I will launch the poll for selecting the correct option. So please select the correct answer in the poll. Let us look at the solution now. So I need to get hold of my pen. Where's that? Yeah. So g prime x is 2ax plus b, and for critical point we need to set g prime x equals 0. So x is negative b over 2a, and g double prime x we need to see now, the second derivative. That's 2a, which is a constant, and the sign of it depends on the sign of a. So if a is positive, double derivative is positive, meaning it's a point of minima, and if a is negative, so double derivative is negative, so it's a point of maxima. So the correct option in this case, and it is not 0 for non-zero a, so double derivative is not 0 for non-zero a. So the correct option amongst all these options is option B, which is no point of inflection for any choice of A, B, C belonging to R. Actually, sorry, this is not the correct option. So if A is 0, then gx is bx plus c, g prime x is b, and the double derivative is 0. So although the double derivative is 0, it is not 0 at one particular point, it is 0 throughout. And why? Because this is a linear function, it's a straight line. In a straight line there is no point of inflection or maxima or minima, it's a straight line. So even though for point of inflection we have double derivative equals 0, but here for this linear function double derivative is 0, but it is 0 everywhere. So that is not a point of inflection. So indeed option B is correct, that it has no point of inflection for any choice of A, B, C belonging to the set of real numbers. Some people selected option C. Even I got initially confused by option C, because A equals 0 gives G double prime x equals 0. But we need to be careful. At a equal to 0, the function itself is no more quadratic, it is linear. Okay, moving forward, we can look at the second question. The function hx equals x cubed minus 5x squared plus 2x plus 4 is what? We need to see whether it is concave or convex and in which region. Once again, I will start the poll, and please select the correct option in the poll. We will discuss the answer now. So again, let us look at the first derivative. So the first derivative is 0. That means we need to find the roots of the quadratic equation. So the approximate values of these roots comes out to be 0.21 and 3.12. Now let us look at the double derivative. The double derivative at 0.21 will be less than 0, and the double derivative at 3.12, the other root, will be positive. Let us see when the second derivative is 0. So that's the value. Now let us look at the plot. Sorry, my drawing is not quite up to the mark. Let me try once again. Maybe this one's a little bit better. I need to draw the axes now. Okay, so that's the plot of the function. Those are the axes, and this is the point of maximum, which is approximately 0.21. This is the point of minimum, which is 3.12. Sorry, not this point itself, but this x-axis. 0.21, 3.12, and somewhere over here will be the point of inflection, which is approximately 5 by 3, which is 1.67. So that's the plot of the function. Now in this, we see that this part over here is the concave part, and this right here is the convex part. So this is concave, this is convex. Now we can look at the ranges given and select the correct option. So the correct option is option B, concave in -1 to 0 and convex in 4 to 5. So option B is the correct option. Moving ahead, question number 3. The function kx equals tan x, we need to see it has a point of inflection at 2n plus 1 pi by 2, or a point of inflection at n pi, or it is concave in this given interval 2n minus 1 pi by 2 to 2n plus 1 pi by 2, or concave in the interval, either convex on this interval or concave on that same interval. I have refreshed the poll for all of you, so please take a few minutes to answer. Okay, time for the solution. Again, let us plot the function. I need to try again. Maybe once again, let me see. I'm not getting the desired shape for the plot. Even AI is not able to help me. Okay, let's just go with this one. I don't think I can do better. So that's the plot of the function, and let me mark the some points on the x-axis. This is 0, this is pi by 2, this is pi, this is negative pi by 2. And once again, we see that these parts over here are convex, these parts above the x-axis, and the parts below the x-axis, those parts are concave. So this is concave and this is convex. So the correct option now will be option B. It has a point of inflection for at n pi, that means 0 pi. So that's the point of inflection. Point of inflection is where the function changes from being concave to convex or vice versa, going from convex to concave. So where the concavity or convexivity changes, that point is the point of inflection. And you can also see, so k prime x is sec squared x, because the derivative of tan x is sec squared x, which is 1 over cos squared x, and the double derivative So the derivative of sec x is sec x tan x. So it is 2 sec x by chain rule and then sec x tan x. So this is cos cubed x. Sorry, not squared but cubed. And this will be 0. Oh, sorry, I am encroaching into question number 4. So k double prime x will be 0 when sin x is 0. And this is at x equals n pi. So that's how we solve for question number 3. Next question, question number 4. Consider the function, it's a piecewise function. It's defined as x squared plus 1 for the interval x less than 0 and cos x for the interval x greater than equal to 0. The set of inflection points of f is given by which of the following options? Option A, 2k plus 1 pi by 2 for all k in set z, which is integer set, or 2k plus 1 pi by 2 for k belonging to integers but greater than equal to 0, or 2k plus 1 by 2 for k greater than 0 union k where k is less than equal to 0, or 2k plus 1 pi by 2 for all k belonging to integers and k greater than equal to 0 union just the singleton set 0. Once again, the poll has been relaunched for all of you. Okay, we will discuss the answer now. So the first derivative, that will also be piecewise. That's the first derivative, and then the second derivative, that's the second derivative. Now x equal to 0, that's an inflection point. And why? Because the double derivative at 0 minus, means from the left side, is positive, because it is 2, it is a constant. And the double derivative from the right side, 0 plus x greater than equal to 0, that is negative. As a result, that's a point of inflection. And also the curve x squared plus 1 does not have a point of inflection, but cos x has a point of inflection. So for cos x, the points of inflection are at 2k plus 1 pi by 2, and these are the points where it actually crosses the x-axis. And the sign changes actually. And at these points, the double derivative is 0. And to see that, let us once again draw the plot. I'm really sorry about my poor drawing skills. Even AI is not able to help me that much. Okay, this should be good enough. So this point is negative pi by 2, this is pi by 2, this is 3 pi by 2. And you see, like from previous questions also, we saw that where the concavity to convexivity changes, those are the points of inflection. So this part over here is concave, and this part over here is convex, and the changeover occurs at these points, pi by 2, minus pi by 2, 3 pi by 2. So generally speaking, at 2k plus 1 pi by 2, at odd multiples of pi by 2. So the correct option is option D. So you see that the point of inflection is at odd multiples of pi by 2 and also at this singleton point x equal to 0. So this singleton set. So at every odd multiple of pi by 2 and for these for the singleton set. An odd multiple of pi by 2 but only for k greater than equal to 0. Why? Because cos x is only for x greater than equal to 0. For x less than 0, the function definition is different. Okay, so we can move ahead. Question number 5. Let f from 0 to infinity to the set of real numbers be a function such that f is differentiable on 0 to infinity. F prime is continuous on 0 to infinity and limit x tending to 0 fx exists. Further, suppose that there exists delta greater than 0 such that f prime x is not equal to 0 for all x belonging to 0 to delta interval and limit x tending to 0 f prime x equals 0. Now define a new function capital F from R to R as follows. It is fx for x greater than 0, it is negative f minus x for x less than 0, and it is limit t tending to 0 f of t for x equal to 0. The options are this capital F has a point of inflection at 0, or it is convex on 0 to infinity and concave on negative infinity to 0, or limit x tending to 0 capital Fx equals 0, or capital F has a local extremum at 0. Once again, the poll has been restarted. Okay, so let us see the correct answer. So the correct answer is option A. F is a point of inflection at 0. And once again, let us just see one example plot. So we can have just like some random function, sorry, not this, which has basically a 0 derivative at x tending to 0. So x-axis and the y-axis. And so at this point, the function at x equals 0, so limit x tending to 0, f prime x is 0. This is the condition that is given. And also this is in the positive half. For the negative half, we have negative f minus x. So that function will be the following. That's going to be this function. So if this is fx, this is negative of f of minus x. And from the definition for fx and negative of f of minus x, what we use is this condition that limit f prime x equals 0 when x tends to 0, this point. And also this condition that for x greater than 0 it is fx, and for x less than 0 it is negative f of minus x. So these are the important conditions we made use and just randomly made a plot, and the point of inflection is at x equals 0. So we are at like the 1 hour mark, and we have 2 more questions to go. This week we have fewer questions than usual. So let us take a short break of 5 minutes and then we will be back. Okay, so I hope everyone is back from the break. We have just a few more questions, two to be precise. Question number 6, the second last question. The function fx equals x sine x is what? We need to select the property concave or convex in which regions, or inflection points, uh, whether it has no inflection point or infinitely many inflection points. So I have refreshed and relaunched the poll. Please select the correct option. Okay, so let us now look at the solution. So we know that x is a monotonically increasing function. So that will not change the concavity or convexivity. And also it will not change the roots, because x is 0 at x equal to 0 and even sin x is 0 at x equal to 0, and rest all of the other places x is non-zero, but sin x, wherever that will be 0, those will be the roots of x times sin x also. So let us draw the plot for sin x. I think I'll copy it from here. Let me just copy paste this from here. This is cos x. I'll shift it to make sin x, because my drawing is anyway not at all good. Oh, let me try to erase these points as well. And I need to shift this over here to get sin x. So this is the plot for sin x, and you can see that this region is concave and this region is convex, and for points this is 0, this is pi, this is 2 pi, and this is the plot for sin x. So you can see that it is concave in 2n pi to 2n plus 1 pi. This is concave, this is convex, and convex is in 2n minus 1 pi to 2n pi. So this option is correct. At the same time, option D is also correct. It has infinitely many inflection points, because at each of these points where the concavity changes from concave to convex, those are the points of inflection. So it also has infinitely many inflection points. So two options are correct for this particular question. Okay, last question for the day and for the course. Question number 7. The function hx equals x cubed plus 3x squared minus 2x plus 5 is what? Convex or concave in which region? Last question, and I will relaunch the poll one last time. Okay, so let us now look at the solution. It's a similar question to what we have solved earlier also, so it should be easy. So we'll look at the derivative, then we'll set it equal to 0. And this turns out to be approximately the following values. Then we'll look at the double derivative. And the value of the double derivative at each of the roots of the first derivative. So this is negative, so it's a point of maxima. This is positive, this is a point of minima. The double derivative is 0 at the point x equals to -1, which is a point of inflection. So I'm trying to draw the plot for this function, and as you have already seen, I am pretty bad at drawing these curves. I'm just not able to get the desired shape. Maybe I'll go with this one, looks pretty decent. X and Y axes, and let me label some of the points. This is 0, the minima is at 0.29, the maxima is at -2.29, and this point of inflection is at -1. And so from the point of inflection onwards, this is convex, and from the point of inflection in this direction, this is concave and convex. So clearly we can see the regions. The correct option is option C. It is concave in -3 to -2 and convex in 0 to 1. So the correct option is option C. So that's it. This brings us to the end of this course. I hope all of you have learned at least some new concepts. Mainly we have looked at limits, at continuity, at differentiability, and properties of functions like maxima, minima, points of inflection, convex or concave functions, and also topics like looking at marginal revenue and cost functions and profit functions, um, elasticity of demand, the functions for demand, price demand functions. So those kind of things we have looked, and how to analyze those functions, how to find the maxima. That's where the calculus part comes in. So that was all from this course. And that's all from my end. And so the course is officially over, but we will have one more revision session for 2 hours. So that is just, we will revise the concepts that we have already learned and see a few more questions before the final exam. So that's it. See you in one final session, but officially the course is over. So if you are feeling confident with all of these topics, feel free to skip that revision week. But if you want to just look have a quick overview of all the topics, then you may join the revision class. Okay, so thank you everyone. Bye bye, and hopefully we might meet in some other course.